Okay, is my PPT visible?
Yes, ma'am.
Okay. Okay, good evening to all students. So today is going to be our first lecture class, and in today's class I'll be just giving you a brief introduction to what this course is all about. So the course code is ECE 4078 MGCB, and the course name is Motion and Geometry Based Methods in Computer Vision. And my name is Anusha Juwarikar. I'm an assistant professor of Department of ENC. Okay, so if my voice is not audible or if it's breaking up, please let me know. Okay, you can unmute yourself and let me know. If you have any doubts or queries, you can unmute yourself and let me know, because I won't be able to see the chat box. So you can feel free to unmute and ask me any queries or questions anytime in between. Okay. Okay, so coming to introduction to computer vision. So I guess some of the students must have taken the program elective on computer vision earlier. Some of you may be new to computer vision. So in today's class, I'm not going to go to details. I'm just going to discuss some applications of computer vision and specifically MGCV techniques. Okay. So when you look at this particular figure over here, okay, when as humans, when we have a look at this particular photograph, we see that our human or visual system is able to detect the color of the flower and the shape of the flower, identify what flower it is, identify the different texture as well as the illumination variations which are present within the image, and also very importantly we'll also be able to make an inference on what is the relative distance of the flower with respect to its background, right? So all these different information the human visual system is able to perceive or is able to understand by looking at a particular photograph or by looking at objects in real life, right? Now, computer vision is all about developing algorithms that is able to do the same as that of the human vision system. That is being able to, understand the shape, the edge information, the texture of different objects, and being able to recognize or identify certain objects, and also be able to understand what is the relative distance or the relative positioning a relation between different objects which are present in a particular image. Okay. So there are so many different techniques in computer vision. I'm just going to have a very quick overview of what are the different techniques, some of the different techniques in computer vision. So one such technique is the image stitching technique. So in this, what is done is, let's say you have multiple images of a particular scene which are taken at different, that is, you have a scene captured by at a particular camera position, and the camera position is, let's say, changed, okay, by x distance, and again the next picture is taken and so on, and you have a multiple set of images, right? So in image stitching, what is done is it basically merges the different views. Okay, so here this is not simply stitched together. What happens is, first we go with trying to identify certain key points given in a particular image or present in a particular image by having a look at what is the edge information, what is the texture information in the image, and so on. And once these key points are identified, we try to relate that with one another, right? Because there would be some overlapping areas in different images, and depending on these are aligned together, and then the image stitching is done. Okay, so here in this example you see that there are only two images given, but you can have a multiple set of images, and these images can be stitched together to get this particular kind of view, like a panoramic view that you see in your camera. This is one example of image stitching. Okay, now another technique is exposure bracketing. So an example here is, let's say you have a particular scene. Okay, and for those of you who are new to computer vision, when I say scene, what I mean is the what do I say, the scene or the background, or what is being captured, the image which is being captured by the camera. Okay, that's what I call as a scene over here. So I have an object along with a background, right? And in this particular image what we see is that this is an image which is a very poorly, or which has a very poor lighting condition, right? So you have an image where it is towards the darker side, and you have an overly so a medium exposed image here, and this is an overly exposed image, right? So if you have such multitude exposure images of the same scene, then those can be combined together, and you can recreate or reconstruct an image with a properly lit, or with a proper exposure image. Okay, so this kind of technique is what you call as exposure bracketing, and this is again one of the techniques that you use in computer vision. Now, another example of a technique is image fusion, or image morphing, also to some extent that comes under the same image fusion or image morphing that comes together. So here in image fusion, it is basically what you're doing is, if you have two images or two photographs, you're trying to blend them together. It gives a certain set of information or details present in a brain, and probably a PET image, which is positron, I think it's emission tomography. It gives another set of information. But for certain diseases, okay, where you see that maybe the progression of the diseases may show only very subtle changes in the modality, okay, in different modalities. So probably fusing different modalities together would give you more information about the progression of that particular disease. So you may be able to infer, or probably the doctors would be able to infer better about the progression of a disease by being able to fuse different modality together. So that is an example over here. You're trying to create an MRI PET image. Okay, for example, an MRI and CT image. Okay, coming yet another example is 3D modeling. So that means you have, let's say, different images of a particular structure. So in this case, it's a house, right? So if you have different images of the house taken at different angles, then that you can use that information to create a 3D model of the image. Okay, so it can be a geometric model where it just shows the shapes and the shape structure information of the particular object, okay, or of the particular scene. Or it can be a texture mapped image where it shows along with the texture, there is the color information and other intensity variations which are present in the image. So these are some examples. Okay, coming to some other applications of computer vision. So here in this image, what we see is what you call as the optical character recognition. Okay, so optical character recognition means, let's say you have different images. where you have handwritten characters, okay, a particular character. So if it's a character 0, it can be written in different ways. And this optical character recognition is all about being able to identify what is the digit or what is the alphabet, which is, yes, is there a doubt? Okay, I'll continue. Okay, so another application of the optical character recognition is being able to identify the numbers which is present in a number plate in a vehicle, right? Now, another example is machine inspection. That is, an example is shown over here. So that means, like for example, being able to detect if there is any holes, leaks, or any kind of defects present in a particular manufactured product. Okay, that's an example. Or inspecting it for quality assurance and so on. Okay, so that's an example. Another application maybe here, there are objects. This is a particular grocery, or let's say a mall where you shop for certain objects, and then so it's in the retail where it is able to recognize what is the object, and thus you can do the shopping. Another example here is the 3D modeling of the medical images. Okay, another example is the automotive safety for automated driving. Okay, being able to identify where are the other vehicles around you, or if there is a passenger, passerby or any pedestrian which is crossing the road or so on, being able to identify all that. And here, this is an example of a surveillance where you can identify or count the number of vehicles which are present in a particular lane, and thus identify how much is the traffic, whether it's a heavy traffic or so on. So these are just a very few examples of where you can use different techniques of computer vision, where you can apply all this. So the main reason of these, so you're definitely, you would be interested in working on something which is related with computer vision, because of which you must have taken this program elective. So if you find any of these applications interesting, or if you have some project or a particular work in your mind, as and when we learn about different methods, or we go through different methods, keep that application in mind, and keep asking yourself how each of these techniques can be used for that particular project that you have in mind, or any work that you're maybe currently working on. Okay, so these may help you. Discussing about different applications may give you different ideas on this. So that was a very brief what discussion on different applications of computer vision. Now, in this course, which is the MGCV course, we'll be specifically looking at a certain, sub branch of computer vision, you can say. So we'll be focusing more on the motion and geometry based techniques used in computer vision. And if you look at the syllabus of the course plan, it is mainly focused around these particular topics which I have listed below. So it's on affine. So we'll begin with affine and projective geometry. What are the different 2D transformations and 3D transformations which can be done? And we'll also discuss a bit about the image filters, the image features which are present, and identifying the key points and so on. Then we'll also discuss about registration. So registration is basically aligning images together, and what are the different ways by which we can do the alignment. It could be a 2D alignment, it could be a 3D alignment, it could be a rigid alignment, it could be non-rigid, and so on. So we'll be having a discussion about what are the different techniques which are used there. Then the next topic that we will be discussing about is tracking. So tracking means being able to track the movement of a particular object. So let's say you have a video sequence, or if you have a set of images, and you want to identify a particular object, or once the object is identified, you want to track where the object is in the subsequent frames of the video, or in the subsequent a set of images that come by. Okay, so that is what you call as tracking, and we'll be looking at techniques where you can track a particular object. And then what we'll be discussing would be about stereosis or stereo vision. So this is all about if you look at the human visual system, we have the left eye and the right eye to see an object, or to reconstruct the 3D, the background. Okay, when we look with both our eyes, right? So we have the information from the left eye as well as the right eye to give an information about what is the distance of different objects with relative to each other. So that concept is what we see in stereo vision also, where you have a left camera and a right camera, which can be used to reconstruct a particular scene in a particular image. Okay. Another topic that we'll be discussing is the structure from motion. So what that means is it can be clubbed together with the stereosis. So basically, structure from motion means that if you change the camera positions, okay, that is, the camera position keeps moving, and from each position you are taking an image or a set of images. Okay, and from that, being able to reconstruct the structure of an object or of a particular scene or a building or so on, that's what you call as a structure from motion, and there are different techniques for that. So we'll be discussing about those techniques. And finally, about arranged data. So range data means it's also called as the depth map. That means you have certain cameras where it is able to detect or capture the depth information, the distance information of the different objects, rather than just the color or intensity. So basically what information you get would be the depth map, and that will help you to identify what is the distance of the object. So these are the broad topics which we'll be discussing in this particular course, MGCB. Okay, now coming to what I'll do is, for each of these topics, I'll just give you some examples. We are not going to go in detail about each of these topics. I'll just give you a very brief, summary of what each of these topics does, or rather, I'll give you just some examples or applications that come under each of these topics. So, first topic, as I said, is the affine and projective geometry. So in this particular topic, you will be learning about what is basically affine and projective transformations, and then we'll be discussing about different filters, gradients, features, and so on. So let me just discuss about this first, and then I'll go to the geometry, affine and projective geometry. So filters means, let's say you have a particular kernel, okay, and you have an image, right? So these filter kernels would be used to filter out or produce a filtered image. So it's like as if you are sliding the kernel. So let's say if it's a three cross three kernel, or maybe it's a 5x5 kernel. So to find the value of the center pixel, when I say center pixel, what I mean is center pixel of that particular kernel, right? So what you do is you just take the weighted average of the kernel as well as the underlying image to find what is the value in the filtered image. Okay, and you can have different types of filters. It may be a convolution filter, or you can use some edge detection filters, or so on. So that is broadly about filters. Then gradient, again, gradient is a technique by which you can try to find out the edge information present in a particular image. And features, there are different image features. What we will be discussing about would be about the SIFT features and HOG features which are present in the image. And these features would help with the what I say the registration or the alignment of different images. So we'll be discussing about these two. Now, coming to affine and projective geometry. So this is an example of a projective geometry where you project the presence of, so if you have an object, you kind of project that object into a plane and then you get a 2D view of that particular object, right? So depending upon where is this positioning of the viewpoint, okay, what is the shape that we receive of that particular object would also vary, okay. So if this particular plane, let's say, is parallel to the image plane, then we can say that there would be a preserving, I mean, the shape of the object would be preserved. Need not be the size of the image that may not be preserved, because sometimes depending upon what is the distance of the image plane and the projection plane, it may be enlarged or diminished, okay. But as long as it is parallel, the shape would be preserved. But if it is not parallel, you'll see that a circle, in this instance a circle becomes an ellipse when you're doing a projective geometry or projective transformation, as you see in this image. Okay, now if you come to affine geometry, this is an example of certain operations that come under the affine geometry of or affine transformations. So let's say this is an original image that we have, right? So the different techniques that come under affine transformation are scaling, rotation, and shearing. So scaling means you can scale it along the x direction or the y direction. That means along the horizontal or vertical to get a smaller image or to get a larger image. So that is scaling. Rotation means you can rotate the image to any angle, okay, just as the name says. And then shearing is when you kind of translate along one particular direction but not along the other, or it's more like translating it or scaling it diagonally, okay. So that is shearing, and this is an example of shearing. So in a fine transformation, what you see is here, if you look at all these three, you see that the parallelism of the lines is preserved. Okay, like for example, if you have these two as parallel lines, these two are parallel lines, those are the same in each of the transformation also, or each of the transformed images also. But in the case of a projective geometry, that does not happen. Like I'll just show you an example in the next slide, that is over here. So in this slide, if you see this particular this particular grid, let's say, and you have four different corners over here, right? So this is an example of doing a projective geometry. So this can be viewed like, for example, imagine that you are viewing it from this point where the black dot is towards the left side, towards your left side, or near your left eye, and the blue dot is near your right eye, okay, or towards your right side, and you're viewing it. So you'll kind of get this view where this seems to be at a larger point, and this seems to be at a shorter distance over here, right? So you can when you're viewing it through this angle, we'll get an image that looks like this, right? Now in this type of projective transformation, what we see is the parallelism of these lines that is not preserved. So here, these lines over here, okay, it's no longer parallel as per the Euclidean geometry, right, over here. Now an example of an affine transformation, in this case, this is the case of a shearing. So here in this shearing example, we see that although we have done a shearing, okay, but still the parallel lines still remain parallel in this case, okay. So basically, you can say that the affine transformation, it is a subset, or it is a subclass of the projective transformation. Okay, and we'll be learning more about these in the later classes. Okay, so just to give you Okay, so after discussing about the different geometric transformations, we'll be going to registration. We'll be discussing about registration. So as I said, registration is nothing but aligning different images together. An example is shown over here. So let's say you have a set of images over here, and these images are a set of images that are taken of a particular airport with some planes in the airfield or the airport. And here, by registering these images, that is trying to identify which are the common points or which are the areas that overlap between different images, we can kind of align these images together and stitch them together to get a much more larger image with a lot more details, as which is shown in this particular image in the right side. Okay, so this is an example of image registration, or it's also called as image mosaicing. Okay, another example which I've already discussed earlier. So let's say you have a set of different images, okay, and from each of these images, it is what to say, it is taken by having a little translational shift in the camera positions between each of the frames or each of the images. So if you have such images, you can easily identify the overlapping regions and register them together to get a panoramic view of the particular image. So that is what you see in this bottom part. Okay, now after discussing about registration, we'll be going to tracking. So tracking means it is identifying an object. So once an object is identified, trying to track the movement of an object, right? So in this example, what you see is the object of interest for us is this particular person over here, right? And this is a football field, right? So we'll be tracking what is, or the algorithm, we want the algorithm to track the movement of this particular player, right? So once it is identified and it moves, so you see that in this frame you have this person moving, and in this frame you have this person moving. Okay, and you can also notice that there is another person who has been identified over here, and here the person is there here, and here the person is here. So tracking is all about identifying the objects of interest for us and being able to track the movement, right? So even as the background changes, or even if the background is complex, the algorithm should be able to detect the movement of the object. So this is one example. Another example of tracking is, let's say you have CCTV images or videos of people in a public place. So let's say it's a mall, or if it's an airport, or so on. Being able to identify a person in a crowd and being able to detect the motion of the person. So that is also very important, right? So this is another example where you can use computer vision to track the movement of a particular object within a crowd. So one thing you have to notice is that these are not simple. So if you have only one single object along a background which is kind of homogeneous background, and the background doesn't change between different frames or different images, then tracking the object becomes much easier, because all that you need to do is identify the background and just subtract the background or so on. But once you have multiple objects that look alike, and let's say you have a background which is very complex and the background keeps changing, then tracking actually becomes difficult. So people have been working on developing such tracking algorithms since a long time, and there are certain very good tracking algorithms too, which can be used in certain different applications. So we'll be discussing about some of the tracking methods. Now, another application of tracking, if you have watched the Avatar movie 2009, so it's about if you look at this particular image. Okay, so this is the actress that was depicting this particular character, and so you have a set of sensors which are fitted around the particular the actress, and the motion of the actress while the actress actually plays out a scene is being captured, and the same is being depicted or reconstructed. Okay, sorry for the noise. Yeah, so the same is being reconstructed in the particular animation movie. So this is one application of tracking again. Another application is action recognition. So here these are when it comes to action recognition, this is something which is coming as an outcome of tracking. That is, once an object is being tracked or the motion of an object is being tracked, in action recognition what it does is it also tries to predict what is the action or underlying action that happens along with that. It is not just tracking the movement, it is also about trying to identify what is the action based on the movement. Okay, so one example would be, let's say, drinking, where let's say there's a coffee cup and the person takes the cup, lifts it up, and then places it down, so that could be kind of identified as drinking. Okay, so that's one application of tracking. Okay, then we'll be going to stereosynths or stereo vision. So stereo vision means, let's say you have different images or different view images of a particular object or a particular scene, then we can reconstruct that using the stereo vision. So as I said earlier, just like how our left eye works and the right eye works in order to reconstruct a particular object. Okay, the same principle is being used in the case of a stereo vision also. So instead of eye, it's going to be a left camera or a right camera, and from which you have a left image and right image which is formed and which is kind of slightly different from each other, and from which you can create a particular or reconstruct a particular image. So here also you'll see that of this particular person, if you look at the left eye and the right eye view, it's going to be slightly different, but from which you can reconstruct the particular 3D image. So that's about stereo vision. Then structure from motion. So structure from motion means the camera position is being moved. So the camera position keeps moving. Each time it moves, it captures an image. And from these set of images, you can reconstruct that particular object. Like for example, let's say this is an example where there is a 240 frame video sequence. So this shows the first frame, okay, where you can see the frontal view, let me call it the frontal view, okay, of this particular object. And then this is the last frame. So this hand keeps on rotating the particular bowl, and this is the side view of that particular bowl, right? So structure from motion techniques would be able to identify the or reconstruct the model or 3D model of this bowl by being able to extract the information from all the frames in between, because basically you have multiple views of the same object. Each view will add in a additional information regarding the position as well as the structure of the image, right? And this keeps adding, and then you can finally reconstruct the image. And these two images over here shows the final reconstructed image. So you have the fingers also along with the ball, and this is the side view, and this shows the top view where this much has been reconstructed. So again, that would depend upon how much of the object is actually being reconstructed, or how well the object is being reconstructed would depend upon how many images are available and how much of new information does each of the image add, okay, and so on. This is another example. So let's say this is the side view and this is the frontal view of a particular object, and you have multiple images in between also, or at different positions in between too. So from which you can reconstruct a 3D model of this particular object. Okay, so here in this example, if you observe, in the top row, what you see is a particular scene where you have the buildings and the road. Okay, and here you have the same scene and a person drives the cycle, and again another scene where this person goes ahead and another person comes in, right? So this is these set of images are real-time images or real life images, let me call it that way. Now, when it comes to movies, okay, if you want to make an augmented video with certain animation characters inserted in that, okay, you can make use of computer vision techniques, okay, to do that. Like, so in this particular scene, what happens in this, if you look at this particular frame, video frame, what you see is that an animation object has been inserted into the scene, right? And then in the subsequent frames, what happens is that this animated what object keeps moving, and you can see that as it progresses, it keeps moving and this goes on, right? So this is an example of an augmented video. Okay, and the last topic that we have for MGCV course would be about the range data or the images, or it's also called as the depth maps. So in this, what we'll be learning about would be how the camera would be able to capture the information of the depth or the distance from the different objects which is present, or a particular object which is present. Okay, and for that you have Kinect sensor camera, so we'll be just very briefly discussing about that too. So this is going to be a 3 credit course, and so there'll be 36 hours for this particular course. And the course plan for this MGCB course, I will be uploading it later today, and you can have a look at the course plan and how the lecture, what the topics and how many lectures and so on would be taken. You can have a look at the lecture plan, which I'll be uploading. Now, these are the objectives of the course. As I discussed, we'll be discussing about geometric primitives, image registration, motion of an object, structure from motion, and about range images. Okay, so basically, after learning this MGCV course, you would be able to identify, or you will be learning different methods by which you can do a 3D modeling of objects from images which are present. Now, again, there are a lot of public data set which is available. Now, when I say public data set, what I mean is data set which is open source. Okay, so you do find various open source data set with regard to 3D shape modeling and with regard to tracking and so on. So as in when as you're learning the course, you can also just try out some of these techniques, or maybe related concepts in these data set, and try to work it out, okay, so that you can understand these better. And this will also help you with your future major project also. Okay, so these are some of the reference textbooks that you can follow. You can just have a note on these textbooks. Okay, if any of you have any doubts or queries regarding any of the topics in the course plan, or how the course plan is going to be conducted, or regarding the classes, or any suggestions regarding anything, you can ask me now. So I see that there are only 55 students who have joined. There are 10 more students to join as per the list which I have got. So if you know any of your friends who were not, who has not joined today, or who will not be been able to join because of certain reasons, please let me know. Okay. Okay, so I'm assuming that there are no questions or queries. Fine. So we'll begin with the first class L1, lecture L1, which is on details on geometric primitives and affine and projective transformation from Friday. We'll start it on Friday. So on Friday, we'll have the class from 10:30 to 12. Okay, thank you.